All right. So like I mentioned, this will be section 7. So this is our introduction to linear regression. And we'll kind of explore a little bit. We'll kind of motivate like we know where this comes from. Know that linear regression is kind of like has been the go-to for statistics for a long time. It's very powerful. It's very useful. It's also flexible. We'll also find that's one of the machine learning algorithms. It really is a machine learning algorithm. Sometimes they'll call it statistical modeling, but really it's a machine learning algorithm. It's just one of the base ones. But what's nice is it's very interpretable. You're able to present like, from the model exactly what's going on, at least not exactly, but like you're able to interpret what's going on to a stakeholder and such. Compared to some other, more advanced machine learning models that we'll see, it's a little bit harder to ascertain exactly what's going on in some of those. I'm speaking to like deep learning and stuff like that, as you guys might have heard at some point in hearing about data science. So it's kind of a great like first go-to. And so we'll kind of get into that. And it's basically, it's relatively simple. Like when you think mathematically, it looks intimidating, but trust me, it's not as bad as it looks. All right. So let me go ahead and start sharing my screen. And just remember, as I get the screen share proper, that these will be the notebook I go over today should be in the resources, that notebook resources I share out. So I just keep repeating that in case people are like, where did you find that? It's in there. Okay. So, so you can see we're going to talk about some stuff, and basically linear regressions is basically all about finding relationships. And so first thing kind of going through like, what you might say is like, okay, well I have, let's say a bunch of data, right? And each of this data, like each data point has maybe like in our project, we'll actually be looking at houses and house prices. So a house feature, for example, would be like, oh, number of rooms, does it have a backyard, all those aspects, how many bathrooms, all that stuff. So those are different relationships, and you want to see, hey, well, are those related to it in any way? This is where actually covariance comes in. So we heard of variance, right? And can someone just kind of quickly say, what is variance? Okay, if summarizing your own English words. And also variance and standard deviation are related. Like basically standard deviation squared is variance.
It's kind of like a measure of how much the data is different from the mean of the data, right? Like how spread out is this data?
Exactly, right? Yeah. Your standard deviation, your variance, basically saying how spread out is your data coming through. And what's it called? It's kind of like describing like, you'll hear spread, distribution, and stuff like that. So the idea is like, how far is it from the mean? So good. And that's kind of like where covariance comes from. So variance, again, variance and standard deviation, very related to basically just square root of one of the other. Our variance is defined basically as this funny math notation. So I don't know who's familiar with math notation. I show this because it's always really useful to like see what's going on. But basically what's going on is that this big old E, if you aren't familiar with it, is sigma. And this basically represents a sum. And basically it's saying, oh, starting from the value I to n. So n being the number of points. So you imagine like if there's n rows of data, that's what that lowercase n is standing for. And you'll see other forms of how this is written, but this is one way to write it. And basically what's happening, it takes your data point, xi. So basically, if the very first data point would be x0 or x1, depending, who you're talking to. Then your next one would be x2, x3, x4, x5, and all that stuff. This mu right here, does anyone remember what mu is?
That's the mean.
Mean, good, right? It's the mean of the whole population. And so this number, this mu, is like a single number. It doesn't change. So basically, like Jenny had said, it's basically finding how far away this minus part, so how far away is the mean from the actual data point. And then we square this. And the reason why we square this is actually trying to get, when we're in a lot of ways trying to get like the absolute difference. We don't care if it's lower or higher. We just care like, how far away it is. So we square this, and then we just divide it by the number of, what's it called? The number of data points. And we just add these parts up. So basically you'd have like x0 minus mu squared divided by n, and then plus x1 minus mu divided by n plus, and so on and so on and so forth. You could also summarize this as put the divided by n at the very end because of order of operations, but the whole idea is there. So that's what variance is. Covariance is kind of similar. You can kind of see like, for example, we'll see covariance, for example, written as like this sigma, this lowercase sigma. X, Y. And basically saying, how are these measures differ from each other or relate to one another? So the idea here is very similar to like our variance. It's like, how do the points differ from the whole distribution? We're seeing how does X differ from Y? And so you can see here, it's like we have our sigma, or sorry, not sigma, our mu X and our mu Y, and those are the means of those populations, of mean of X and the mean of Y. And we want to see how those relate together. So you can see that kind of motivation, and that's why we call it covariance. Okay. So the meaning of this basically is saying like how they correlate together, how they match with each other. So if you have positive covariance, it means that they, as one increases, the other one should increase as well, at least in value. A negative covariance would do the opposite. Basically, as one increases, the other one decreases. So one thing you should know about this is that this is more mathy terms. So basically, it can go from negative infinity to positive infinity. Basically, it can be really, really, really big, or really, really big, or really, really small. So the thing about this is that if you had different covariance, it's hard to tell exactly how does one covariance compare to another one. If you had like, sigma of xy and sigma of xz, it might not be super clear exactly, well, how much bigger is that? Because it can go all the way off to infinity. So one solution we have is something called correlation. And we'll actually use basically something called Pearson's correlation. So you'll see this a lot with this lowercase r. Now note that this is not the only way to measure correlation. This is one of the more common ones, but there's a bunch of other ways you can measure this and stuff. And if we were doing more statistics and going in statistics to PhD, we might actually explore more about exactly what it is. But also know you can come across this yourself, and you might find a situation where a different correlation factor makes sense. But I show you this really scary looking math stuff. The main idea here is just knowing that you can kind of see, oh, that's kind of similar to the covariance right here, okay? And the only difference is on that denominator right here, we have this aspect. And basically it's just scaling it down. So what happens is that it turns out instead of going from negative infinity to infinity, we actually allow us to go from -1 to 1. And this allows us to not consider the units. So if we're considering dollars or number of rooms, it'll always be scaled down between -1 and 1. So we can now interpret this correlation. And this is where this classic, I think this is actually directly from the curriculum itself. You can see that there's a basically perfect positive correlation. And I would actually say it's not quite perfect because I think it might be a little off. But basically a correlation that's very close to 1 means that as there's an increase in value by one factor, the other one increases by the same amount. Okay, so you basically have this perfect correlation going through. Remember, it's scaled down too. So it's kind of like by the same amount. Basically, they're both going up in the same, by the same amount. As we get smaller and smaller correlations, as we approach 0, you can start seeing this, well, each data point doesn't quite increase on a nice line. Sometimes an increase, and generally an increase like in the x direction will mean an increase in the y. But if we went from here, to this point, we increase in x by this amount, but we can actually see y either stay the same or even went down. And that's because each data point is a little fuzzy. So you'll tend to see correlations that are close to this. You rarely see a correlation perfectly 1. And usually if you see something that's really strongly correlated, you're like, that seems a little suspicious. I might need to check if those are even the same variable or we're measuring in the same way. 0 means no correlation, basically randomness. There's no way I can determine as I increase x, will y increase. That's essentially what this 0 part, explains. And then the opposite here is as we get negative correlation. So basically as you increase in x, you start decreasing in y. So you get the whole part in there. Basically, our 0 is kind of like saying there's just random noise. And then 1 meaning that, we have a very strong positive correlation. Basically they both go up. A negative correlation would mean that they're basically as 1 increases, the other one decreases. So inversely related. So let me ask you guys, which one do you probably want to see for prediction? If you had x is saying, oh, this is my thing I know, and I want to predict y, okay, which correlation would you want? What kind of value do you think?
The perfect correlation.
This one right here? Yeah. Yeah, I know. Everyone's really really fearful.
Positive or negative, yeah. As long as it's perfect.
Yeah, the perfect, positive or negative. Good, right. And so the negative one, sometimes people will say, oh, we want positive, but negative is actually just as good too, because we can actually perfectly predict this. The way I kind of explain this is kind of like, if you have a good friend who's got similar taste to you, right? If they like a movie, you'll probably like that movie. That's a high correlation. That's kind of closer to 1. But you also, if you have a friend, or or maybe not a friend, but you have someone who has completely different tastes from you, and every movie they hate, you love, and every movie they love, you hate, then you have a negative correlation. Well, that's like the perfect predictor, right? You just got to watch whatever they don't like to watch. And basically, you'd know you'd watch that stuff. So that's kind of something with that negative correlation is going on. Okay. So this kind of introduces us like, okay, cool. Like we can see this relationship, and you can already see like we're starting to form, building this relationship on the plot. So we can actually do this into statistical learning. So, excuse me, as an intro, kind of like when we go into statistical learning, okay, we have to say like, okay, like what are the things we're measuring? And it's really important to understand like what are the things that we're measuring versus what are the things that we're trying to like test against. And basically we have variables in 3 different flavors. If you're familiar with the sciences, these will look very familiar to you. Like even like my 7th, 8th graders when I was teaching science lab, I drilled this into their heads. I'm sure like your 7th grade teacher at some point drilled into your head, whether or not you remember it. But the important part is that you have 3 different flavors: an independent, a dependent variable, and possibly a controlled variable, right? And so the independent variables are the ones that you can change. And this is where like I say like the ones that you can change, it's more like these are the things that change that will have an effect. Sometimes it's not super clear. For example, like time, we can't change time. Time moves on. We can't do anything about that. But it's something that we can measure saying, oh, as time moves on, how does the things are affected from that time? So usually time, for example, is an independent variable. Our dependent variable is really what we're trying to measure. It's like, what's the thing that we care about? What's the thing that, you know, taking all these different independent variables and we adjust them a certain way, could we predict this outcome? So the idea here is the dependent variable depends on what those independent variables do. That's kind of like the name in there. And of course we have controlled too. This is kind of like more of a sciencey thing, but I throw it out there, is that controlled usually means that like these things don't change, or we set this specific variable the same. So we're only looking at houses in California, or only houses that are in this specific zip code, or only houses with 5 windows. That's essentially like would be a controlled variable. You're kind of setting in stone. We don't usually, I mean, we kind of use this term, but it's not as common. We're usually talking about dependent and independent variables. Okay. And then statistical modeling. This leads us into what this actually is. It's essentially just a function, or sometimes you'll hear people call it a mapping, if you're really like mathematical. But basically it's a function. It's some kind of like formula that defines a relationship. And I shouldn't even say formula, because it doesn't necessarily have to be a formula. It basically says, when you put these things in, what is the likely outcome? So if I have a house that has 5 bedrooms, you know, 2 bathrooms, you know, a backyard, and, you know, zip code 95, whatever, right? What is the price of that house? Well, we expect that house to be this price. Will it be that exact price? Probably not, right? It'll be maybe higher or lower, but we hope that if we do that for many houses of those same exact type, you get about the number. And that's why we call it statistical model, because basically you're not really sure exactly if it's going to be the exact thing, but based on the data you have, you can hopefully predict what's going on. And that's really what statistical modeling is. And one thing that we'll talk about, like I said, is linear regression, but there's other statistical models that we can create. Okay. And so here, for example, you can see there's actually a regression line, which is what we'll talk about today. Basically, this X part right here is the height, and then here's going to be weight. So this, for example, might be a graph of saying how heavy someone is based on their height. So some people, you know, are more stout, some people are more skinny, you know, like, so you might have some people who are really tall who have actually very low weight, and some people who will be taller, well, you will tend to have a higher weight as you get taller because you just have more ability to be heavier, right? But you won't fall perfectly on this line, but we can hopefully predict on this. And basically these points right here, your intercept, your slope, that's just describing this line right here. And hopefully that line is describing this model, or this data, and we call this line actually the model. Okay, sound good to everyone? Yeah, any questions so far? Cool, all right, awesome. And oh, hey, Aubrey, I didn't see you come in, and Carly too. Aubrey's, I don't know if you guys have met Aubrey yet. Yes, okay. I think she's joined in one part. Cool, yeah, she's our master online teacher. There she is. Yeah, so let's see here. Sorry, I lost my train of thought now. Oh, some processes and terms. So sometimes we'll actually call these things, we'll kind of go back and forth, so you are familiar with this. We'll talk about parameters to build the model. So those parameters are kind of like, you know, for example, I said intercept and slope. We'll also say like those are features versus targets. So our features are usually like, you can think of our independent variables. Those are the things that we kind of are like saying, oh, if you adjust these things, an outcome will happen. And our target is our dependent variable. So we usually want to have our just one dependent variable. We might take other models and try to predict other like other targets, but in general, we're saying there's one target that we're trying to look for, and we have multiple features. In this case, there's only one feature, the height, and then one target, which is the weight. And again, parameter is just another way of saying like, okay, what are the things that are going to use to build this model? And this depends on what kind of model you're building. You'll also hear that we'll do like model validation, basically saying like, you know, how well is this model as we're kind of making it better and better. This is kind of sometimes considered like learning. So statistical learning basically just means like we're just trying to make it better and better. We basically try a model out and you're like, hey, does this model work well? And you're like, it doesn't really work well. We'll talk about what that means. Because it doesn't work well, it's like, all right, let's adjust it and like, go from there. It's like, okay, well, that works a little bit better, but let's adjust it again. That's the learning process. So whenever you hear like machine learning and statistical learning, that's all that means. You're just trying to get a better and better process or better model. Cool. All right. So now to the meat, right? To our linear regression. So here's a basic linear regression. You'll see things like this all the time. This is a very nice linear regression. Usually they're not as nice and neat and everything, but that's okay. In this case, we see there's only 2 dimensions. We're only going to talk about 2 dimensions today. Tomorrow will be multiple dimensions, multilinear regression, which will be fun. But once you know the basic 2D, it's actually not that much more difficult to add into multiple. So essentially we have here on the x-axis, that's usually where we always put our independent variables, our features, and then on the y-axis is our target itself. So that kind of is this mathematical notation, what you normally would see. And each of these little red data points right here are essentially just different parts in there. And essentially what you do, the model, basically the algorithm looks like, you're looking at all these data points and you say, okay, what's the best line that will fit right through here? And that's called our regression line, or sometimes called our line of best fit. Basically, which line fits the best in this model, which explains the data the best. And so once you have this, you're like, cool, you have a line of best fit. It turns out too, is that we can solve this something called analytically, which basically means if you have all the data and you know what kind of model you want, you can always solve it. Now, always solve it for mathematicians is not the same thing as actually being able to solve it. It turns out that when you actually want to solve these things, it might take actually a lot of processing power. It might take more time. So we'll actually find other strategies. But for the most part, when you're applying a linear regression with a package, you probably don't have to worry too much about that necessarily. Sometimes you have to kind of consider it as there's more and more features, and we'll talk about that, especially tomorrow. But for the most part, you can pretty much say, oh, it's able to be solved. Okay, so this kind of explores the motivation. The reason why we're talking about linear regression, because like, as you probably have heard, there's a lot of other algorithms you can do. One of them, you know, like for example, deep learning right now is really big. Like all this like really cool stuff. It's like, well, why don't we learn that first? Or why don't we talk about this? And that's because linear regression, first of all, has been like around for a long time. So it's well understood. It's well developed. There's a whole bunch you can talk about. Sorry, my window kind of went down a weird place. But it's kind of like our first go-to for a model. So it's relatively simple to implement. It's relatively simple to like pull out information from it. Compared to some other models where like it's not as clear, like why did it do this specifically? So it's a lot harder to debug. And this is also, to be honest, just more understandable for other people who are not in data science. Maybe they're statisticians, maybe data analysts. They probably came across regression analysis at some point. So it's something you can use to communicate. So this would be a great like start for, what's it called? Like for most like start of your data science projects. Okay. Oops. So this goes into creating our linear regression line. So there's a lot little stuff going on here, but don't freak out, right? So right here, basically we have our actual lines. This is basically the equation of a line. So if you remember back into like y equals mx plus b, if you're in a different country, you might have to actually learn it a little bit different. So sometimes you'll see it referenced in different letters, but the main form here is that y, which is our target, right? X is our independent variable or a feature. Okay, in this case, I capitalize it because I'm kind of hinting back it's actually a matrix if you have multiple, but you can think of this as essentially just one number or a set of numbers. And A is going to be our slope, and B is going to be our y-intercept. So you'll see me kind of reference it in this way. And you'll see it referenced in different ways. Turns out too, our slope is just equal to our Pearson's correlation times the standard deviation of y, so how y varies, and the standard deviation of x, how x varies. So it's kind of nice to be able to just pull out the slope from here. And essentially you can create this going through. And this is why, for example, like it's actually relatively simple to create these, what's it called? Linear regression. Essentially, if you know Pearson's correlation, which we just basically go through all the data points, right? And the average. And then we have our standard deviation, which we can basically define without having to find the average itself. We can also, do that. Again, these are all just done by computers, but you can probably figure out, you can probably think about how it's calculated. We can just pass this in, and then we got our equation, right? The biggest thing is going to be the b, which is the y-intercept. That's the part you would basically have to solve from, say, okay, we have the slope, we have x, we have y, we got to solve for b. Classic kind of algebra stuff. I make it sound really simple, but obviously there's a little more you have to tell the computer to do. The nice thing is that for the most part, you don't have to do that by hand or scratch. You usually use a package to do this. But this guy right here, I want to kind of point out the different parts. You'll see this notation. This is not my own image. This is something I actually found online. You'll probably find something very similar. But basically, you can see here, they'll use W. And again, this is kind of a hint to be a little bit like their matrices. You'll see W a lot as matrices, sometimes called weights and stuff like that, depending on your machine learning algorithm. But just know it's basically the same thing, is that we have our linear regression line, a line of best fit. We have this y hat, and so y hat basically represents the model. So when whenever you see y hat, you should instantly think, oh, that means model. That's going to be our linear regression line. Our W0 is that y-intercept right here. Basically, where is the intercept on here? W1 is going to be that slope. Basically, what is the slope of that line? And then times x will basically say, oh, whatever x you put in there, whatever feature you have, in this case, x, the explanatory variable, independent variable, your feature, whatever you put in for x, out comes out a y hat. So the y hat will always be on this line, okay? Now, in order for us to actually see how well our model is, we need to see how well it does against data points. So you can actually see here these little squares, these green squares here. They're basically representing the data points. And so you notice that almost all of them are not on the line of best fit. And you can see this one's pretty close, but even that's kind of off, right? Depending on how you squint at it. They obviously have some width and everything like that. But you can kind of see it's not quite right. So what we do here, and that's where these little lines coming from those those green squares are coming from. Those little lines are representing how far off is it from this line. Basically, remember, y is our target, what we're trying to explain. So we can imagine we have a point right here. It's okay, we have a value. Let's just pretend, I'm going to start drawing a little bit. Is that, let's say from this point right here, we have our x value. Okay, and let's say the x value is 3. I don't know, 3 feet or something like that. So, and our y is our weight. But the point is that we have some number here, and we say, okay, we put 3 in for x. We have some numbers here, we put it together, and we get some value. Let's call y 5. Okay, so our y hat is equal to 5. So this right here would correspond to 5. Okay, but our actual data point, this is a weight of an x of 3. Its actual value right here, we're just going to say, we're going to estimate that's 6. So it's a little off. So we say oh, we're off by 1. So this little line going from the square to the linear regression line, this little line is representative of just 1. It's a unit of 1. Oh, we're off by 1. Okay. And then you can see over here, it's oh, we were off by 0.5. This one we're off by 2. This one we're off by 3. So you basically look at how far each data point is away from your linear regression line. And you say, okay, those are all the different parts. These are all my different errors. And this is what we call a residual. So each one of those points are just called a residual. Basically, how much it reside, how much is left over from us not being able to explain. So if you were perfectly on this line, you smack right down in the middle, you'd have a residual of 0. If you were off really far off, your residual would be really, really high. Okay. So this is actually how we use to measure how good is this function, how good is this model. And so this is where we'll actually take the residuals. We'll do something called sum of squares. Basically, instead of just adding up all the residuals, going over here, what we could do is oh, this is off by 1, this is off by -5, this is off by -2. We could technically just add them all up. What might be the issue if we just added them all up just from their natural form? We got to guess.
If some of them are positive values and some are negative, you might get stuff canceling out.
Yeah, you might get canceling out. So you might say, oh, I got a residuals of 0. All my residuals are perfectly fine. Because remember, our residual, if we got everything exactly on that line, if we added up all the residuals, it'd be 0. So if you happen to get something that's really close to 0, oh, sweet, that means I'm really good. But obviously, it's wait a second. So one solution we could technically do is absolute value, right? So we could make it all positive, so we could add them all up. Classically, there's a few reasons why this isn't true. One is just literally just easier for calculation, stuff like this, and just kind of the history of it. There's other mathematical reasons you could probably go into, But what we end up doing is just squaring it. Since every negative number squared is always a positive number, and we're only dealing with integers, no weird imaginary complex numbers, we can just square them and say, okay, you square each part. So you say, oh, it's a difference of 2. Okay, we'll say the square of that residual is 4. And we say, okay, this is a 0.5. Oh, that square is like 0.025, and you add them all up. So one factor for squaring is kind of nice is that it punishes very big values. So if your value is really far off, let's say you're off by 10, instead of just saying, oh, that's a value of 10, you now have a value of 100 for that sum of square. So basically it's like, oh, that value is really, really bad. It's giving a lot of, it's giving a lot of error. Where if you have a very small error, your small error is going to be like, oh, it's going to be a little factor onto it. That's another reason why we do squares. And one thing you'll sometimes see, I'm going to draw this on here, if you ever see this like diagram out in the wild, just quick like thumbs up. Who's ever seen some diagram like this before? Maybe like, okay, cool. So one thing you might see is not just this line here, which is the residuals. We'll see actual squares written like this. Yeah, I've seen some nods. Good. So Eduardo's definitely seen this. So you'll usually see it this way, and that kind of like represents basically you're adding up all the area. So you're trying to minimize the area that's in here, and basically it's just representing saying, oh, it's the residuals squared. Okay, so that's what I mean the sum of squares, which you'll see me talk about all the time. Basically, you're just squaring the residuals and adding them all up. And this is what we call our loss function. Oh, yeah, I think I skipped over a part. So I think this loss function here basically is how we define how good is our function or how good is our model. It's kind of confusing why we call it a loss function, but you'll hear this over and over again. That's kind of the terminology, and we're stuck with it kind of deal. I'm sure someone can tell me there's a real reason why it's like, oh, loss, because of this loss. It doesn't really matter, right? The point part is just vocabulary. I could have called this flippity flop and it'd be the same thing. So the point here is this loss function is saying how good is this function doing? How good is this model doing? And so we can say, okay, well, the loss is how your sum of squares, okay? And what this really ends up happening, if you look at this, is actually thinking in the ways of saying, we can think of it in terms of the worst model. It's saying like, okay, if we had the worst model, what would this be? And if we can get better from the worst model, that's essentially what we have. And so when I hear this, I think the curriculum actually calls it like the worst model. And people say like, what do you mean worst model? What does that mean? Well, the worst model, and they say this in terms, but hopefully this makes sense, it's basically just the mean of the y. So instead of drawing a nice line that's kind of increased over time, you just say, all right, what's the average, let's say like this was weight. What's the average weight of everyone in the US? Okay, it's like, I don't know, let's say 175 or something like that pounds. You say, oh, 175 pounds. Okay, well, that's just going to be right here. And that means anytime you get a person, just say 175 pounds, 175 pounds, 175 pounds. If it's a normal distribution, basically you're going to get 50% going to be above, 50% going to be below, and you got it just right. In a lot of ways, that's kind of like the worst model. Like I'm saying like, well, technically it does fit, but like it's easy to calculate, but you're not going to get most people right? So that's what we're comparing it to. And so you can see here, for example, if we had a nice like parabola, like it would basically, not the best thing. So sometimes you'll hear this reference, like we're really taking the worst model and comparing it with our linear regression. And basically our linear regression is trying to do better than our worst model, okay? So I hope that kind of makes a little sense. But I want to throw it in there because I think the curriculum kind of mentions about the worst model, and I think it says it more in terms of like words. But our worst model essentially is just that average because you don't even like try to take in any information. Okay, so this kind of goes into like, okay, like we can actually define this, right? We basically say, all right, make a line, okay, and we can actually solve for this line perfectly. But usually we'll take a line and say, oh, is that good? Not quite. We'll readjust it, and the way we readjust it or make sure like that's just the line of best fit is we judge it off the sum of squares, basically those residuals squared, add them all up. So this kind of comes down to like, awesome, we can find a nice model, the line of best fit, okay, sounds promising. When does linear regression work? So one thing you can kind of quickly see is this going to work if you put a linear line or try to put a line to try to model this parabola? Yeah, obviously not, you're all shaking heads, right? So it's funny, my wife has seen me like do this before. And like she said, it sounds like you're talking like Blue's Clues, where you're like, is this gonna fit? And like, no, like I'm waiting for people to say things. But anyway, yeah, there's no way a line will ever fit this. You can maybe get close, right? You maybe get like a line like, oh, maybe like like over here, like, start kind of low and go up and can kind of get it, right? But you'll never be able to fit it perfectly, right? So this kind of says like, well, sometimes linear regression just will not work. And so here's an example. Why is this like this? Oh, well. You can see here an example is that this linear regression, not bad, but you can kind of see there's some things that kind of stick out to me. You're just like, it doesn't quite fit exactly. We can see some parts over here. So like, when do we say linear regression can work? So the first obvious one, like we just mentioned, is, does it have a linear relationship? Does it look like a line? If it doesn't have a linear relationship, like a parabola, linear regressions are not going to work. Relatively simple, right? So on any kind of guesses, like we'll talk about this actually further in the course, but like what could be some possible solutions we could do if we wanted to make this data fit on a linear, or like use a linear regression or modify linear regression or something. This is just brainstorming kind of stuff. Anyone got an idea what you might do?
Could you split them up into two separate sets?
That's good. So maybe part of it's linear, right, Jeffrey? Like, and you say, all right, let me take this part that's kind of linear, split up. That's good. Yeah, you could do something like that. Maybe try to do multiple linear regressions to kind of fit this through. Anyone else got an idea what you might want to do? That's not an easy problem. Yeah. So one thing you might want to do is, and this is where like, I think this is why most people don't think about this, it's like, I can change the data. I'll just change the data and transform the data. That is a thing you can do. We'll actually talk a little bit about like how to do this, like transformations and stuff. And it's actually relatively, as long as like, you're transforming the data and you're transforming everyone equally, but you're transforming it all of the data set, you can actually do that. So for example, if like, and we'll talk about this later in the future, but I'm just gonna give you guys some ideas, like it's not, all hope is not lost. You could take, for example, instead of the data here, where it's going like, in this parabola, if you know parabolas, that's y equals x squared, like something like that, you can take the square root of each value. And that should hopefully actually end up putting your value closer into a line, right? So for example, if you had something like, what's the first one? It's 49. 49 is 7 squared, right? So if my value is like 49, I take the square root, right? That will give me 7, and the other one will give me 7. So it can basically use that to predict on top of it. Another way is actually taking the linear regression line and essentially modifying the linear regression line, which is what we'll see again in like, I think module 3 is when we talk about this. And we'll actually see, maybe it's module 4 even, I don't know. Anyway, but you actually modify your linear regression using mathematics, essentially, and then you can fit it all on the data. But basically, modifying the data or modifying linear regression is actually equivalent to each other. Just kind of like which way you see it, same side of or different sides of the same coin. Okay. I just wanted to throw that in. But for the most part, you want to make sure your line is relatively linear. So you can see here, this is more exponential. Our next part is our normality assumption. So one thing to kind of note is, this is a part that I know that a lot of students get a little like, what is normality? Like, why do we have to do normality? So on normality, right, our statistical distribution, our Gaussian normal curve, and thumbs up, everyone knows what a normal curve, right? I think we talked about this too, right? Yeah, good. So a normal curve, in case you kind of forgot or whatnot, is basically this nice, beautiful bell shapes. You hear the bell curve, normal curve, a Gaussian. Basically, it means that you kind of can do our nice little math in it. Basically, the average is right at this peak, and then on the tails, basically, these we can write this mathematically out. We know how far it will drop off depending on the standard deviation. So you can basically see this nice little curve. Now, this right here is not a normal curve. You can see there's some outliers kind of bumping around here because it looks mostly normal, and then you can kind of see on the edges over here, it kind of like has these extra bumps and stuff. So this is what we talked about when something is normal. Now, one thing I want to emphasize is when I say this is normal, it's talking about the residuals. So it's not the actual data itself. The data doesn't necessarily have to be normal. We're really talking about saying, are the residuals normally distributed? And that's the important part. So what I mean by this is that, let's see here if I can do this right. This, for example, like if you look at the residuals, you might see that more residuals are on the higher end on this end versus on the lower end. So like maybe you have a lot of high end residuals versus the low end residuals. That wouldn't be a good part. So I guess I could, that's not really the best graph. I really should throw in a graph in here at some point to kind of emphasize this. I don't have to draw it too much. But if you imagine like a nice little plot, and we have like, let's say our line of best fit, let's say we mathematically found out that's the line of best fit, right? And then I have my data points. And so if my data points, if my residuals are kind of like off the side right here, okay, and they're mostly clustered on the edges like this, and then maybe like a couple, most of my residuals will actually be kind of like either way too high or way too low. Essentially what my my plot will look like if I did a histogram of the residuals would basically say you have some that are really high, or sorry, really low, and then not too many, and then really high. And so that's not a normal curve. So if I were to draw this guy right here for my residual plot up there, that's essentially what's going on. It's like, well, that's not a normal distribution of my residuals. That means I can't really necessarily use our linear regression. There again, there's some ways we can kind of modify this. We'll talk about a little bit tomorrow as well. But that's an important part. It's not that the data is normally distributed, because the data can be non-normally distributed, but the residuals are fine. It's really about the residuals itself. Okay. Does that make sense to people? Give me a little thumbs up if that sounds good. Yeah, go ahead.
So the residual is the difference between like the line and the point, right? So it's looking at those differences and plotting it on the like graph to look for normality.
Yeah, so like your residual for like this point would be like this would be my residual, and then that one would be like this one. And so I'm actually plotting out those individual points, like, oh sorry, those individual residuals. So this would be a very large residual like over here. So it's like the size of the residuals, or I guess, sorry, yeah, this is like the size of the residual. This is how frequently it happens. Okay. So yeah, cool. I know sometimes this can be kind of confusing too, like when you first see these plots, but they're really useful for us to do. And we'll see a couple other things we can do. Cool. Any other questions? I'll go a little more into this, but yeah. Okay. And honestly, as you guys kind of do the project too, and you're like, wait, you know, I don't quite remember, or I didn't realize I didn't understand it, bring it up, ask questions, right? Because this is probably the hardest part for a lot of people to grasp, okay? So that's why it matters. There's a few ways you can actually plot out to see if this is a normal distribution. So you can see here, this is a nice normal curve, normal distribution, right? And you can use like, you know, a histogram. That's what this guy is, right? So we can do like a dot hist on like the residuals and stuff like this. So this is one way. Another one is called a QQ plot. And so one is like a histogram, like I said. The other is to do a QQ plot. And note these are visual tests. This is not saying, oh, there's a like if it's not perfectly on here. You're saying is like, is it normal enough? Which seems very kind of like laid back. There are some ways you can numerically do to test normality. However, this is where like if the data isn't quite normal, you still might want to try out a linear regression to see how well it tests out. And this is why it's a little fuzzy. Say what is normal enough. And it's a little subjective and stuff like that. But you can see here on a QQ plot, basically it's plotting out how far it would be, like how far these values are from each other. So they're a little bit difficult to read. I would suggest like kind of just looking at a QQ plots and like when you see a nice histogram, do a QQ plot and just get a feel for like what this looks like. But you can essentially see is that our line right here represents if everything is perfectly normal. Okay, if things deviate from the normal, you actually see it go off this line, this red line here. So for example, you see here that we have almost nothing in the tail, so it's very spiky. This is called something called high kurtosis. Basically, it's very, very tall. It's not this nice smooth bell curve. Okay, it's not really a bell. It's more like a Washington Monument or something like that. And you can see here is that these tails on the QQ plot basically deviate greatly from this red line, which again represents the normal distribution. Here you can see it more of a skew, basically where things kind of get pulled off to the side over here. So instead of having this nice bell curve, something that's a little extreme, sometimes you might see something that's closer to like you'd have a kind of bell curve and then you might have something that kind of trails off like this, okay? So it almost looks bell, but kind of trails off like this. You can see here is that we have too much in the beginning going on. And then in the middle, it's kind of bell curve, but really not. And you can see it differs from here. So really you want something that's close to this line. Will you get something as beautiful as that top one over here? No, like you won't get it nice and beautiful, but you might have a little bit on the tails, on the extreme ends. This might be true for like outliers and stuff like that, which we'll talk about like feature engineering and stuff like that next time. But basically it's like, oh, you might want to remove the outliers or consider those, like, are those outliers actually part of this model or are they describing something completely different? So in that case, you might want to remove them completely. So yeah. Anyway, these are a couple ways you can actually visually test, say, hey, is this normally distributed? Cool. Any questions on this these two graphs of it. Yeah.
So, and this is a really broad question because I don't like completely understand it in terms of like data science and stuff yet. But I mean, there's many different kinds of distributions. So if something's not like a great fit, do you just go on to like another distribution in data science, or do you really try and like manipulate things like we've been talking about, removing outliers and stuff to fit it?
Yeah, good question. And this is where I think people have certain preferences over other people sometimes. For example, one thing you might do, or I tend not to like to transform data too much because you could technically try to transform data and it's perfectly legit, but then it's hard to interpret because you're like done so many different transformations. It's like, what does this even mean anymore? And usually to me that suggests that it's probably not a best way of approaching it. Sometimes you can do it well enough. It's like, well, the data is not quite, like in this case, we're talking about normal distributions for the residual. It's like, oh, it's not quite normal, but it's normal enough. I'm like, okay, we can probably proceed, but just kind of be aware. The other part, what I suggest as a data scientist is, how do I say this? Is that like, you'll hear me say this again and again, is that as a data scientist, like it sounds really dumb, but like you are human, right? Like you actually have a lot of ability to say, well, okay, it doesn't quite fit, but why? Like, is there a reason? Am I seeing some extreme values for a particular reason? Maybe, for example, in the survey, you see these extreme values, like, well, maybe this is coming from a certain set of people that are not really belong to the overall survey myself. And that's like, oh, I should remove these outliers, or, oh, you know what, maybe we need to consider these people separate from, or like, you know, whatever the values are, it doesn't have to be people. But like, it's like, oh, we need to consider these houses as a separate part, or we need to consider this feature and stuff like that. There's a bunch of ways you can kind of go. And that's the thing, data is really messy. The data is not really nice and clean and everything like that. You could go into like another other learning algorithm and everything. I see a little chat icon. Let's see. All right, cool. Aubrey says, there's also an entire realm of hypothesis testing. Yes, so there's a whole different thing for when you talk about hypothesis testing, which I think comes up in module 3. So, and we're in module 1, so it's got some time until we reach that point. But there's definitely like other ways you can approach like non-normal. Like I said, like there's ways you can approach it. One strategy is to try to transform the data. Other times like, all right, let me take the data the way it is, maybe transform a little bit, but apply a different strategy or a different method. So that's a good question. And that's a good overall general like truth like in data science. Cool. Any other questions? I think I saw someone else unmute themselves. Mm-hmm.
Yeah, so I was wondering, so these are the histograms for the residuals of something, right? And it's showing that the residuals themselves are non-normal data, at least in the bottom two is, I mean, I just want to make sure that that's what you're saying. Not, this is not the data, this is the residuals of the data.
That's right. That's right. The data might look like this, but the residuals for your linear regression might be normal. And that's the part that we talk about as the normality assumption for linear regression. That's what we're talking about, is the residuals themselves.
This is a plot of the residuals. Are these plots of the residuals or are these plots of data?
In this case, I think this is just data in general, but this would be a plot of your residuals.
Oh, the right side is a plot of the residuals, right? No, wait.
Yeah, this right side is literally the same data over here.
Yeah, and one is one the Q plot, QQ plot, and the other one's histogram.
Yeah, this is on the right side here. You guys can see the cursor, right?
Yeah, but it's like yeah, but it's not labeled exactly. So, right?
It's a little harder for you to see over here. Yeah, but this is our QQ plot.
Right. I mean, yeah.
Mm-hmm. Yeah, and you can
make a good assumption, but it doesn't show. You know, like you have to scroll up a little, and then you say I see it's histogram versus Q. Yeah, I'm just trying to clarify. That's all.
No, perfect. Okay, cool, awesome. Yeah, cool. If I move on then, or
yeah, so it's good. So I see what you're saying is what you want to do if you can't tell for sure is you run the QQ plot analysis, and you see a non-linearity in that. You know that it's definitely non-normal. Is what you're saying. And this, I don't know, to me, the QQ almost, I don't know what those are, but it's like cumulative distribution. You almost see since you see the two slopes, it maybe suggests, two different, let's say, two different effects going on at the same time. That would be kind of, it's interesting to see that. So I'd be curious to see how you can interpret that. Because, like in a cumulative distribution, you would see, if you see more than one slope, it could even suggest bimodality, two different causes for the data. So then you start looking as to why there's two different slopes. And you don't throw anything away. You just say there's two different effects going on, and you would interpret it that way. That would be how I would look at it. The other one on the bottom, I haven't thought about how that would be interpreted, but anyway. Okay, that's all
And I see Aubrey. Thank you, Rebecca. And Aubrey, do you have something to add into that?
So the QQ stands for quantile, and you're comparing your observed quantiles in your data to the hypothetical quantiles of a normal distribution in this QQ. You can make QQ plots for every distribution under the sun. And whenever you're testing, oh, is this a Poisson distribution? Is this a Weibull distribution? Then you're going to make a QQ plot and have a statistical test to compare what you're observing to what it could hypothetically be. So in this case, you're seeing the different slopes in the QQ plot. You can literally interpret it as if it were normal, it should have had, like if you're seeing a positive slope in the QQ plot, like that middle one, there's less beef in the tail, the lower tail of the observed data than there should be. When you are making a QQ plot on anything, trying to see if it's normal, you're always going to see data clustered around the center of that line. But you can really tell the difference between normal and not normal when you get into the tails.
Thank you, Aubrey. Yeah, and that's a good important part to remember is that these QQ plots aren't purely for normal distributions. They're just another visualization. Just like histograms are not just for normal distributions. They're just a way to visualize, you know, in this case, the residuals, but it could be of any data.
Yeah, I mean, it's much easier to, what I'm trying to say is as a tool, I like those tools where you can see with your eye very easily where there might be changes of the distribution, because that kind of suggests, again, like if you're looking at an effect, I'm trying to get to like, well, how would you interpret it? And if you look at an effect, if there's two slopes, what I'm used to is if you can find a way of plotting it that helps that easily with an easy eye, like sometimes the normal distribution is here is exaggerated. The top one is clearly normal, the one is clearly not. But sometimes it's a little bit more, let's say you have two normal distributions on top of each other, but you don't realize that they're kind of like aggregated together. You want to try, I'm looking for methods where you can say, oh, there's actually two distributions in here, and therefore they may come, it's not in random processes, it should be just a normal distribution. If it's non-random, it means it's just two things going on that are really separable, potentially. And that's what I'm kind of looking for, whether you can use a QQ plot in that way.
Yeah, definitely. And I think you're kind of like getting to the point, like it's like looks close to like normal distribution, right? So like you have like, this is like a good normal distribution, but you might have something that's like a little bit like,
a little bit like, exactly like that. Right.
And you would see like,
joins.
and you would see kind of like at the end, it wouldn't quite get right there. Or I guess it might be the other direction. But the point is like, you would start to see, like Aubrey was saying, like on the tails is when you probably would see it the most.
Yeah.
And I think, is that right, Aubrey? I see. But
maybe
yeah.
not with that, what you wrote, but yeah, something like that. I mean,
So QQ plot is not going to help you find by modality per se. It will just tell you, man, this is really weird and not normal. But you're going to be able to use a kernel density estimator or just graphing your usual density function to find out your bimodality. But fear not, density estimation is coming. Kernels are coming, but if you're looking at it and you're just like, I think it might possibly be normal, but the QQ plot's kind of iffy, you can run a Shapiro-Wilk test, which is specifically a statistical test for normality.
That's right.
okay.
And so again, this is like a visual test for you to do a quick, like, does it look normal? And it's like, oh, like this clearly is not normal and stuff like that. And that's where between histogram and QQ plot is really just showing you those parts. But like I mentioned, like, and Aubrey just said, you can actually run direct tests and say analytically, say, hey, is this normal? Like, how normal is this? You know, what's the, like, how far off are you? And that's something we'll definitely go into, I think, with module 3. And kernel density estimation, that's coming like right after this. Well, actually, I think it is module 3 too. Module 3 is when we talk a lot about statistics and stuff like this. I'm saying, like, you know, going deep into it. Yeah.
Yeah. Okay. Well, that same question will come up for me all the time is I'm looking for tools for which it helps the explainability of any model. And, you know, the things that I'm used to are a little bit different than this. But if there's new tools that I can use that will help you explain there's more than one effect going on, I'm not, the data's not, is blurred by two different things going on. That's kind of like what I'm really looking for. So this question will come up again and again. I'm just going to give you that warning.
No, that's good.
As we start to go into this, yeah.
Mm-hmm. And that's where we'll get, like I said, like again, module 3 is when we'll talk about a lot more statistical tools and stuff like that to pull out that information. Obviously, like this is like one of those things like, oh, like which one do we talk about first? You know, like do we talk about all statistical tools and then talk about this part, or do we talk about linear regression, say how do we do modeling? So it's kind of like there's a few things, like for example, I'm kind of like skimming over that we haven't reached yet. But at least to be able to produce a basic model, it's like, okay, this is the idea of normality and stuff like that. There might be for residuals, like the residuals are probably will notice it a little bit quicker. I don't know, that's debatable. But for other distributions, like if you're looking at data, like if you're looking for a bimodality, or like that's definitely a tough thing for you to kind of just pull out. But there are like you said, like tools and stuff like that we could use into it. But yeah, cool. It was a good segue though, even if it's not necessarily linear regression itself. Cool. All right. And so good. We have a last few 5 minutes, so this is actually perfect. So our last part, our assumption for linear regression, just to kind of remind a little bit, we had normality assumption, and then we also had, is it actually a linear relationship? Our last one is our heteroscedasticity, which I can never say the first time, right? You also can, I believe you can spell it with a K as well. So like, I just love this, just like it's a beast of a word. But basically what this is going through is saying, how is your residuals spread out from the linear regression line, so your line of best fit. So the way, what you really want is something called homoscedastic. Basically, when your regressions or your residuals are basically randomly distributed across from your linear regression. So if I actually go up a little bit, so I'll show you these parts. So this is, again, a plot of the residuals. Important to note that it's not the data, it's actually the residuals. And basically it's saying how big the residuals are. This is as we kind of increase like X and whatnot. And you can see here, the residuals kind of do more of kind of this flaring out, or in the opposite way, they kind of flare in versus this homoscedastic. We want homoscedastic. And I'll show you a little bit. I had this going up. Actually, I wonder if I put it underneath here. No, I didn't. Past Victor wasn't smart enough to do that. Okay. You can see here, I'm going to just get rid of this guy. All right, so you can see here, this is our little plot, and you can kind of see is that this will be not homoscedastic, this will be heteroscedastic, because what's happening here is that if you look at each point over here, okay, these residuals are very, very large, right, up here, but as we get closer over here, you'll actually see the residuals are relatively close, right? So what's going to happen is that if you do the residual plot, you'll actually get something that will look closer to like this plot over here, where basically your residuals are relatively small, very close to the linear regression line, and they kind of flare outward because essentially as you go out and out, your linear regression line technically is still the line that best fit, but it does a worse and worse job of predicting these other data points. And so this is something where you want to make sure you actually have homoscedasticity in order to say your linear regression line is actually a useful model and going to explain your data. Okay, so I have a few more examples. So here's a few things you might see. This is what you might have more of that flaring out part. You might also have something where the residuals don't quite follow. You can kind of see these points, these green points. I think it's actually from the curriculum itself, but it basically has this more non-like random uniform distribution. If you see more of this pattern, it means that maybe your actual data is not a linear line as well. So this is really useful. Now, this will be done like after the fact. You do your line of best fit, plot the residuals, and say how do my residuals like are distributed. So here you actually want, this would be homoscedastic. And you kind of see similar. Basically, your residuals are more or less randomly distributed. Some are kind of high, some are kind of low, but they're more or less random. If you start seeing a pattern in that distribution of residuals, like they're really high ones as you go, as you increase your feature, then it's like, okay, maybe there's some other thing going on here that my linear regression line is not going to pick up. Okay. Cool. Any questions on this guy? Other than how to pronounce it, I can't tell you that. All right, cool. So let's do a little thumb check, right? So thumbs up if you're feeling pretty good with it. Sideways, you're like, I get it, but maybe you need to review some more. Thumbs down, this was a complete, like, I have no clue. All right. I like to say, I don't think anyone's ever going to do this because, like, you guys are all really nice. None of you guys are going to be like, oh, Victor, I don't understand a word you're saying. Oh, no, it's okay. But seriously, though, as you go through it, if you have questions, especially if you want to export parts, like that's the fun part about like all of this is that there's so much we can kind of go into. Like Rebecca was asking about going deeper and say, okay, like how do we look at this distribution. Because it's all connected together, we'll kind of touch those parts. And as you kind of go through things too, there's other research too. Like you can kind of use other resources, see other explanations and stuff like this. For example, I kind of quickly went over heteroscedasticity. There's this great article that I really liked that kind of talks about like heteroscedasticity in regression analysis. Like you can kind of go through and talk about like, discuss a little bit like what this is and why do we need to care about it. And this is just linked in within the notebook itself. Cool. All right, everyone. Well, I guess we're kind of at time. Rebecca, you have something to say?
Yeah, it just was your, so this is in your notebook. This is in your repository, right?
No, it's in this, what's it called?
Oh, in the resource, okay.
Yeah, I'll put all my notebooks, so anything you should see like that we do in presentation, it should all be put in there. It's kind of organized.
Okay, yeah.
Yeah, and I think if you go into data science basics,
yeah,
and then linear regression.
Yeah, you've selected out for us before, but yeah, that's. I was just wondering where that was. Yeah. Okay.
No problem. And I think it's also on the Learn homepage. So if you go into like, I think you put like repos or something along those lines. If you scroll in there, it'll also be a link in there. But if you ever need to find it, just message me and say, hey, what was that link again? And I'll message it out.
Well, is it possible for us to know which one you're going to go over before you go over it? And maybe you already said that before, but that way we maybe could follow along. I don't know if it's helpful to follow along.
No, that's a good idea. Yeah. No, that's actually a really great idea. I haven't done that, but maybe I can do that. So
it's already in there. I mean, it's prepared, so it's not like.
Yeah, and I might make slight changes before we actually go into it. Like, oh, you know what, I made a mistake before, or I want to add this part in here. But for at least tomorrow, this multiple linear regression notebook, that's what we'll go over. So yeah, you're welcome to check it out.
Yeah. Okay, perfect.
Cool. Awesome. All right, everyone. Well, I'll go ahead and stop it here, and I will see you all, I guess tomorrow. Remember, 12 p.m. Eastern time, we have our Friday fields, and we'll talk about the project then.
Okay.
Take care.
Okay, thanks.